In today's lecture, we're going to follow on what we learned last lecture. In the last video, we looked at, we defined the commutator and looked at how that sort of related to incompatible observables. Now, today we're going to discuss uncertainty. And if you think about it, the fact that we saw last time that commutation related to incompatible observables and the fact that you couldn't really measure two incompatible observables in the same system without destroying information about the one, you kind of, if you accept that, it's kind of natural to expect that this commutation relates to the uncertainty or what you can know about certain things. And it turns out that there's this relationship that says the uncertainty in some observable A times the uncertainty in some observable B is always going to be greater than or equal to 1/2 the expectation value of the commutator between those two observables. This is actually, Heisenberg's uncertainty relation, but that's the more familiar with position and momentum as our observables. This relationship in terms of the spin 1/2 operators we've seen, an example of that is this, where the uncertainty of a spin measurement of spin in the x direction times the uncertainty of the measurement of spin in the y direction is 1/2 the expectation value of their commutator. And we saw in the last lecture that their commutator is IH bar S sub z. So we have this uncertainty relation. If we take out that IH bar, the magnitude of it, we get the uncertainty in Sx times the uncertainty in xy is always going to be greater than or equal to h bar over 2 times whatever the expectation value of our Sz is for a given system. So if we look at, for example, a spin up in the z direction system, we've prepared our beam of atoms in a spin up state, and we want to know the uncertainty relationship for the Sx and xy operators. Well, the uncertainty in x times the uncertainty in y is going to be h bar over 2 times the expectation value of the uncertainty in the spin in the z direction operator. If we're in the spin up state, the expectation value for that spin up operator is just h bar over 2. Take that, the plus bra and the plus ket, and sandwich that around the s sub z, and we get h bar over 2. So that means that the uncertainty in Sx times the uncertainty in Sy is always going to be greater than or equal to h bar over 2 all squared. And we have an uncertainty relationship. The uncertainty in the z direction is going to be 0. We saw this a few videos ago when we were looking at the RMS deviations and such of measurements. If we prepared a beam in a spin-up state and measured the spin in that direction, every measurement we would make would be spin up. If we idealize our measurement system, so there's no noise or any errors in our actual setup, every single measurement would be h bar over 2, and our uncertainty in that z component would be 0. However, if that's the case, then what that says is the uncertainty in Sx and xy can neither one of them can be known with any certainty. And this uncertainty relationship sort of describes that. We can't know, if we know S sub z, we cannot know with arbitrary precision Sx or Sy, right? This, and again, what I want to stress here is we've assumed a perfect measurement system, right? So there is no noise in our actual measurement setup. This is an ideal measurement. We still can't get past this fundamental uncertainty. And we can never, so that means we can never know all three of our spin components in our spin 1/2 system, which is kind of weird if you've been using this sort of classical, semi-classical idea of spin that is some vector that points along a given direction, and if we measure it in the x, it's pointing in the x direction or something like that. This is saying that the spin doesn't point along a given direction. If we measured spin up in the z direction and think of that as a vector pointing upwards in the z direction, well, that would say we know the x and y components. They would both be 0, and we can't say that. So this is kind of saying that we can't exactly think of spin as this vector that we know in these three dimensions and we know all the components of it at a given time. What we're actually measuring is those the spin components, but we can't measure all of them without destroying information about the others. Another way to think about that is if we consider the magnitude of the spin vector, right? So typically with vectors, if we want to know the magnitude of vector A, say, what we would do is take the inner product or the dot product of the vector with itself and square root it. That would give us the positive sort of length or magnitude of that vector. If we want to take the spin of our spin system, we can sort of write it as a vector as the Sx operator times the x hat unit vector, likewise for Sy and Sc, and take that, define an S squared operator that's essentially S dotted with itself that looks like this: Sx squared plus Sy squared plus Sz squared. To sort of get, all right, what's our magnitude of, if we take the square root of whatever that operator gives, we get the magnitude of our spin. So that operator, if we write it in the matrix representation, would look like this. We take the h bar over 2 squared from all of those operators out. Then we have Sx squared, Sy squared, plus Sz squared, all written in matrix notation. If we do those matrix multiplications, we see that each squared term there, Sx squared, gives us the identity operator, likewise for Sy and Sz. So that S squared operator actually ends up being 3 h bar squared over 4 times the identity operator. So let's look at two things to note of that operator, the S squared operator. The first one is that it's proportional to the identity operator, which means that it commutes with all other operators. S squared commutes with Sx and Xy and Sz. Right, so it's proportional to the identity operator. It gives you back the same eigenket or whatever ket that you input to it. So that commutes with everything. The other thing we want to notice is if we look at the magnitude of this, we take the square root of S squared to get the magnitude of S, and we get root 3 h bar over 2, which is greater than h bar over 2, which is the magnitude that we measured for all of our components whenever we measured one of them. It was always either plus or minus h bar over 2. So that spin being larger, the magnitude of the spin being larger than any of our measured components means that that spin is, again, not pointing along any of those axes, x, y, or z. So we have this weirdness if we try to think of this as a vector pointed in some direction, right? We can think of it sort of, if we really want to stick with that thought, as some vector of length, root 3 h bar over 2, and let's say we've measured it in the spin up in the z direction, we know that tells us that the component in the z direction is h bar over 2, but it's processing somewhere along this path here, and that means we don't know what the x and the y components are if we know the z component. So we have this sort of fuzzy vector where we know we can know one of the components really well, but the other two have this uncertainty where we don't actually know what they are. So there's this kind of breakdown between, if we think of spin angular momentum classically as some object with mass that's spinning, we can define that angular momentum as a vector with components, all of them known in a given direction. In this quantum mechanical spin, we cannot do that. There is some uncertainty and some that we cannot know about at least two of those components.